Okay, great. So let's begin. So we started the review from last night, and as mentioned earlier, we are starting with the question I'm looking using the relation from Kango. So he plotted these two functions. The other one is x is equals to 3 minus y squared, and the other one is for x is equals to y plus 1, the straight line. So when you plot this, the question is only saying that the region bounded by the two graphs, by the graphs. So to bound, of course, as we discussed last night, it's basically just to enclose or the two graphs form the boundaries of that area. So the only area here that you can see bounded by the two graphs. So I'm just going to draw or sketch through the two graphs. So the first one is this one here in blue. So this is the cave part. And then we have the other one is straight line, which is this one. So when you look at these two graphs, clearly the only space that is closed in, boxed in, let me not say boxed, let me say closed in by these two graphs can only be this area here. So this becomes the area that we are actually looking for. So this is the area that they are asking us to find. So to determine what that area is, we see to say we have to do an integral. But remember what we discussed. If you're going to find the area, let's say this is the area A there. So the area A has to be equal to the integral controlling the boundary. Since this is in terms of these graphs that we have here are in terms of this, what we have here is x a function of y. It implies that we are actually using y as the variable here. So the two functions, which one comes first? Which one are we subtracting from the other? So you want the one that is more positive. And when you look at the way these functions are, what you should observe is that the curve part is the one that is more positive as compared to the straight line. The straight line is this side. It's like if I had something like this, and then you have the other one like this, clearly this graph here is more positive as compared to, so this is more positive as compared to this one. So with that in mind, what I'm going to do here is I'm going to take this one as the positive one, and I'll take this one as the alternative, not necessarily as the positive one, as the one I'm subtracting from, as the one which is bigger. So I'll take this to come first. So I'll say if this is the f of x, and this straight line is the g of x, so that what I'll have is f of x here minus g of x. So I've selected f of x such that it's this one here. So apart from this,
Sorry, I'm still to understand why you say that other one is more first that one.
why?
I'm saying, can you please kindly repeat I'm going to use first?
Okay, so here's the thing. If I have, let's say, one graph like this, these are now in terms of the y-axis, as in their variables, the functions of x. And then you have another one like this. And then you wanted to find the area bounded by the two functions, the two graphs. So that becomes this area here. So let me label this one as g of x, and I'll label this one here as f of x. So when you come to find the area, what you have to see is one seems to be better than the other. I want to say one thing here. It's sometimes you might actually miss which one is greater than the other. Because the condition for when you're writing this is that if f of x is greater than g of x, then we end up with f of x minus g of x. But what you have to see here is that if you solve these functions, let's say f of x is greater than g of x, but you you did not see that looking at the functions, because you can see just by observing, by as in by looking at the equation, sometimes it might not be easy for you to interpret. So let me writing g of x minus f of x. What do you expect to be between the solution? Let's say if this is x, so between the two solutions, you guys predict the difference. Can you guess what the difference will be? Well, let me start with a demonstration. So come back to this one. So let me start with a demonstration of one of the questions that we did. So we did, I want one where we were sure about everything that we got. Let's pick the first one, this one. So in this case, we sought to say the two functions, we had that one and that one, are these two. Just want to show you this difference of solutions. We already know the solution of when we say f of x minus g of x. But now I'm just going to swap them. Let's say I was not able to conclude clearly which one is greater than the other. Let's say I decided to swap them, so that instead of doing this, what if I said g of x comes here, then minus f of x? What would be the result? Well, in this case, it's the same thing. Everything here is really the same. Notice what would happen. Now you'd have x minus x, that is, then minus x squared plus 2 with respect to x. I'll try to be a little bit fast. It's a question that we did last time. So here we're just trying to see the effect of swapping those. Okay, so from the integral, this is minus x to the 2 over 2 minus x to the 3 over 3 minus 2x from 0 to 1. Of course, the 0 part reduces to nothing. Then we put 1s. We have minus 1 over 2 minus 1 over 3 minus 2. Okay, so we're ending up with this one where here is minus minus. Let's finish it up. It's going to be 6 here, 2 here 3 times, 2 here twice, minus 2, 1 there, 12 times, that was 6, then minus that times 2 there, that's 12. Observe the answer. This is going to be minus 13 or 6. Found So for the question, when we did the correct, when we position them in the correct position, look at the answer we got. We got the same thing, but it was positive. By just changing the position, let's say by failing to we end up in thinking. So what I'm trying to say is, even if you were the one is greater than here, you should still come up with the same question. Because if you were to start by here is on top, or the one that comes first, and then the function comes later as the care, to just mean most likely your R will be negative. And if it is negative, you're looking for area, which is scalar quantity, you just state it as a positive thing. Have you got that? Yeah. So in this case, of course, to find the positive solution, the k has to be the one that you subtract from. But even if you use the other alternative, the only thing is you're going to find a negative answer. But since it is area you're looking for, which is a scalar, you have to state your answer as a positive in the end, even though you find a negative solution. Okay. Any other questions there?
Apart from that, I saw that you have an intro. That's the
I
one that
am not
you
getting that clearly. Can you type it very quickly? You seem to, your background is a little bit noisy. Just try to type it very quickly before I proceed. Okay, so while I'm waiting for his question, so let me just write down what you're going to do here. I've labeled these. The curve becomes the one you're taking as f of x. So that is x minus y. X, not x, that's 3 minus y squared. So this is f of x. Then from this, we have, not f of x, f of y. I wrote f of x here. Sorry, this is f of y. And this is also g of y. So this is f of y minus g of y. Okay, how can you correctly tell which one should be the upper bound and the lower bound? Okay, I thought it was just from explaining that even if you miss which upper is lower, you still get the correct answer. So idea here, we are looking at it where this is yeah, at so look at where something it was everything functions of x. Our expressions were functions of x, but now these are functions of y. So I've rotated it such that x, the one which is more like where you'd have y here, and then y is the one in this position where you'd have x. Clearly now I hope you're seeing that this curve is the one which seems to be the upper bound. Now here, of course, because it is in terms of x, you're not really looking at upper bound and lower bound. You're looking at to the right and to the left. Which one? Let's say the eastern boundary. Which one is the western boundary? So that is what you have to see there. So let me rotate it back to its original orientation. This original orientation. And like I was explaining, for this type of problem where functions, the curves are functions of y, not functions of x, the bounds are seen as the easternmost boundary, which is this one. So this is the positive most boundary. And then the other boundary is a little bit to the negative part. This would be the western boundary or the westernmost boundary. Have you got that?
yes, sir.
Yeah. So when functions are in terms of x or functions of x, then the bounds are in terms of upper and lower. But when they are in terms of y, then you're looking at to the right and to the left. Okay. So now that we've answered that, let's put a few more things. So like I was saying, the area here will be the integral from a to b, and then you have you're looking at f of x. I keep writing f of x, sorry, that's f of y minus g of y, and then dy. So we know what these functions are. So I won't integrate it, I'll just put it to a position where you guys can actually finish it up. So you have f of y, that is 3 minus y squared, then minus g of y. G of y is y plus 1. So you have y plus 1 here. Then, so what is inside? I'll leave it at this stage, minus y minus 1 dy. These are standard integrals that you can evaluate. But of course, the only thing that you have to get is a and b. And like we saw last night, in these type of questions, they won't tell you what these boundaries are, what these points are, because you can easily evaluate them. These are points where the functions um, are actually equal. These are points where the functions are equal. So you're moving from this point to somewhere at that point. Just want to be careful. Of course, it might be different if the function, let's say if this was something like going up to somewhere there, then you might say, okay, if you come only up to this point from this point, you might be limiting yourself to maybe just this area. You might be not that area. You might be limiting yourself to maybe just this. So you have to be a bit careful here. But the idea here is this line cuts the curve before the curve turns. So perhaps something, let's say something like this. Before the curve turns. So when you pick this point and that point, it actually does encompass everything that is between. Okay, so we'll see more problems where you have to do a little bit of extra work. So because it's when those two curves are equal, we end up with the curve when is equal to the straight line y plus 1. So of course from here, solve this quadratic to find the two values of y. The smaller one among the two will give you the value y here. The bigger one will give you the value y here. The bigger one will give you that uppermost line here. Okay, so any question there? Okay. Now for tonight, I want us to look at something that is a little bit more tricky than what we started with. So I want us to look at functions where now you have to do a little bit of extra work. Consider two functions. F of x equals to just x to the power 3. And then the other function g of x. And then for g of x, you have this is equal to, let me just say, x. So suppose you have these two functions. And then the question is, find the area bound by the two functions by the graphs. How do you find the area in this case? Well, if you try to create a sketch of the two functions, look at what you end up with. So I'll start with this one. I won't try to show how the sketch comes out. I'll just try to place it there. So if what we have is the coordinate axis, we have this and we have this. Observe that that graph there, if you try to sketch it, it's going to be something that comes down like this, and then it crosses the x-axis right there, and then it goes down like that. So let me use something like this. So you have this, then you have that, and comes like that. Okay, so something like this. Okay, yeah, that will. Okay, so this is something that we have. So this is the graph of um y is equals to. So you can say this is y is equals to x to the power 3. Now, what are we seeing? The next one is this one here. G of x is equals to x. So here, of course, we say this is just y is equals to x, and we know how that graph goes. So let me just extend this one. Let's say it continues to go something like this. And let me extend it down here and say it continues to go something like that. So when I draw my straight line now, so let me just do this and scale this down a little. Okay, think a little bit more. Okay, so yeah, something like this. Okay, so when I now draw my graph y is equals to x or g of x is equals to x, we know to say it's a line that passes right through that point. So we get something like this. when they talk about the area bounded by the two graphs, what are we going to see here? Well, bounding the area bounded by the two graphs here, you have to see that it's actually two parts. The first piece is from here. You have this area here. Let me get this in red. The first area bounded is going to be from here, this part, up to that point there. That's the first part. The second part is going to be the other part, which is the upper part. Note that even this piece here, it's also bounded by the two graphs. See, this is what makes graphs like this one a little bit tricky, because how do you actually find the total area bounded by the two graphs? When it was just one piece, we saw it was straightforward what you had to do. But observe this part. You have two pieces, and both pieces are bounded by the two graphs. How do you account for them? Well, just like before, the first part is to know how this is going to be. Firstly, you still want to use the same formulas. The same formulas will still work, but you need to know what this point is. You need to know the value here. You need to know the value also at the uppermost point at the there. You need to know what that value of x, the value of x at that point is. Then the last one is, of course, the value of x at this point when things swap. Now, what you want to do here is instinctively, you want to say that area is equal to the integral, and then just like before, you want to have the upper boundary minus the lower boundary plus the lower boundary. But what you have to observe here is the functions are swapping. What is the upper boundary changes. When you move, if I say this is point A and this is point B, let's take the origin here. I can just say that's where x is equal to 0. Observe that as you move from A to B, so when you're moving from A to B, not to B, to x is equals to 0. When you're moving from A to x is equals to 0, the upper boundary is going to be f of x. The lower boundary is g of x. But observe what happens the other side. When you now move from 0 to b, the boundaries have swapped. The one which is now considered the upper boundary is now the opposite. The upper boundary is now g of x, and the lower boundary is now f of x. So try to see that this is actually what happens there. So because of this same behavior, this maintaining this equation to get the answer will actually give you something that is false. It won't even give you to say negative because let's say when you get when you miss which one is on top and so on, we sort of say you just get the same thing but just negative. In this case, it doesn't even give you the correct thing but just negative. It just gives you something wrong altogether. We can even try to play around so that we see the exact thing it gives you. It's something that is a little bit funny. You can see what it is. If you insist, I can still show you. But what you have to see is you are then forced to perform the integral in steps. First, evaluate the first step as you move from A to 0, with f of x being the upper boundary. Then next, evaluate the second step from 0 to b, with now g of x being the upper boundary. So what am I saying? I am saying that in the first part, I will evaluate my area, or let me say, just get this. So in the first part, I'll move from A to 0, and my area now, the upper boundary will be f of x minus g of x dx. So this is where the first part will end. But I have to add them. Plus, I continue. Now I have to perform the integral. The other one ended at 0. So I'll start from 0 and now I'll go all the way to point B. And this time they have swapped, meaning now I'll correctly put the one which is on top, which is g of x, then minus f of x. This now observe accounts for that swap that has occurred. So this is how we perform the integral this time. Any questions there?
So, sir, you have to add.
You have to add them, yes. There are two pieces. It's area. So it's this area plus that area.
Oh, all right, all right.
Yeah. So the only thing left is to know what A is and also what B is. Now, how do we find A and B? And was it not even 0? Because here we saw to say this is just 0. What if it wasn't 0? And of course, we just see that those are the 3 points when our functions are the same. The other function is f of x is equals to x cubed. The other one is g of x is equals to x. So these are the only areas, or when they are the same, that will give us what A is, B is, not B, A, and the part where that middle point, and also that last point labeled B. So you just have to equate them. So you have x to the power 3 when it is equals to x. So we see that we end up with x to the power 3 minus x is equals to 0. Or you know how you work out expressions like this. One thing that you should never do is cancel out x here. X to the power 2 minus 1. I've factored it out. Common mistake I think people used to do here, but I think people only make this mistake in high school, where you actually cancel this divide outside it does out. You know, to say at this level, you don't do that, you lose a value. So when two things are multiplying but equate to 0, it implies that either x is equals to 0 or x squared minus 1 is equals to 0. So that from the second part, we have x squared is equals to 1, or x is equals to, now when you take the square root both sides, you're going to have plus or minus 1. Notice that now you get the three values of x is equal to minus 1, x is equals to 0, and x is equals to 1. This accounts for A for the middle point, gives us correctly that for this case, this is 0. And the last one there, this gives us what B is. So our integral now is going to be the area is equal to negative 1, 0, of x to the 3 x. Then the second part, now from 0 to 1, the swapped positions, it's now minus x to the 3, then dx. Okay, so any questions there? So here, of course, I think the tricky part was just knowing how you interpret those two different sections and how you combine them to get the total area. Do you guys need me to finish it all the way from here? Or you guys can finish this? Should I finish it together?
Yeah, still not better, still not better.
We can what?
I think we
You can
can
finish.
Or we finish it right now together? Okay, let's go on. So of course, for the first part, when x is 0, we see this all dies out. So the one that survives, so it's going to be 0 minus, when x, I haven't been integrated yet. Let me integrate first. So when we integrate, we get x to the 4 over 4 minus x to the 2 over 2. 0 minus 1. Then plus, we have x to the 2 over 2 minus x to the 4 over 4. 0 1. Insert the limits now. When x is 0, the whole thing just dies out. So we get 0 minus when x is minus 1. This becomes, because this is x to the 4, minus 1 will die out there, leaving us with only 1 over 4. Again, this is squared, so it becomes minus. And this, the minus will remain minus there. The minus, when you put it under the square there, it will die out 1 over 2. Plus the other side, the one that survives is the first one. When x is 1, we have 1 over 2 minus 1 over 4. The one when x is 0. So this is all that remains. So this will be minus 0. So of course we see this is minus. We just do the math now. Let's see. Okay, so let's see what we get here. It's going to be negative. Let me see. It becomes 1 over 2 minus. Yeah. So observe this part. This is going to be, let me see, this is over 4, 1, this is 2, minus 2, and then this is plus, same thing here. This is over 4, 2, 2 there, and then minus 1 here. So you get minus, with the minus on top, that becomes positive 1 over 4, and then plus, this is going to also be 1 over 4. Those two pieces, in terms of this this graph that we plotted, this graph is symmetrical. That is why those two end up having the same area in the end. So it's because the graph is symmetrical. So we ended up having the same area. Okay. So yeah, in the end, this ends up giving us, we just adding this. So add the numerators, we end up getting 2 over 4 or 1 over 2. So that this is just 0.5 square unit. Okay. Now I do have a question for you guys. What would be the mistake? I just said the area, had you ignored the fact the upper and the lower do interchange there, what would have been the result of such an expression? Let's say if you integrated from minus 1 all the way to 1, and keeping top and as the one as f. Can you get?
So can you repeat the question?
I'm saying here in our solution, we observed that we have to treat this as two parts. Integrate from a to 0, from -1 to 0, find the area there, and then integrate this side from 1, find the here, and add them. We sort of say this is how you are supposed to do it. My question is, what if you did not do this? What if instead of doing this, you only what look at the change, the one on top swaps when you go to the other section. We just did from -1 all the way up to 1 without considering what happens at 0 there. What do you think would have been the answer of this integral?
I think you wouldn't have gotten the area. It would have been 0.
Yeah, this one would end up actually giving you a 0. You can try that and see what you get. It would be something, it would be wrong, but I think it will actually give you a 0 here. Okay. Another thing that I want to just point out here is when you look at this part, I did say the solution that you end up with is something symmetrical, as you saw even in our solution. You're ending up with something symmetrical. Now, what's the idea here? See, this case, if you're dealing with such a problem, because of symmetry, instead of actually evaluating from A to 0, and then also from 0 to B, you can actually just pick one part and say, okay, I will actually just evaluate from 0 to B. But since even this will give me the same solution, I'll just double my answer here. So you could have also found the answer by dealing with this problem as from 0 to B, and here maintaining what is happening to say that, okay, the upper for this part was the straight line. So the upper there was just x, then minus x to the 3, as in minus f of x, then dx. But because you're just picking one section and trying to utilize symmetry, it means that you have to double this. This will give you the same as well. This is another correct approach that you can take in working out this problem. But this only works for problems where symmetry is actually achieved. Any questions there? Okay. That seems to be okay. Now, how about this one? For the last question for this part, the next thing that we're going to move to is going to be about volumes. Volumes of revolution. That's what we're going to start doing, I think, tomorrow. But here's something that I want you guys to try out. So this is find the area bounded by the graphs, and I'll say f of x is equals to, I can even say y is equals to sine x, and y is equals to cos x. And then I'll say for 0 is less or equal to, let's say less or equal to what? Let's say less or equals to, that's x, which is less or equal to, we can go up to 2 pi. Yeah. So let's take that to be the solution set. Now, the question is, do we want all the way up to 2 pi? I think 2 pi might be too much. Okay, let's look at them. So we have this, and then we have this. And we have this. Okay. So 2 pi elapses. So let me just take it out to 6. So 7. Even 360, I think 360 would have also worked. Even 360 would still give you the same solution to 2 pi. Okay. Yeah. So find area of the two graphs, but just take note, we are being restricted by this solution set. Okay. So I'll let you guys try out this. Please send the solution in the group as soon as you find them. Then I will respond to you guys. Yeah. Let's end here tonight. Do you have any questions before we end? Okay, so yeah, let's take that. Don't forget to invite your friends. Yeah, invite your friends to join us. The more the merrier. Now, guys, have a good night.